Good morning, my dear student. Today I'll be talking about linearization of a nonlinear system. So linearization of a nonlinear system. Let us see uh, what is a linear system. We have already seen. Say for example, we have dx1 by dt. So this is equal to small ax1 plus bx2. Then we have dx2 by dt. This is equal to cx1 plus dx2. So this, this can be written in matrix form like this: dx column matrix dt. This is equal to a is the coefficient matrix and x is a column matrix. Column matrix vector. So your a is the coefficient matrix. This is equal to a b c d. So this is your coefficient matrix. Such system we call it linear system because the here variables are x1 and x2. They are involved in the first degree only. There is no x1 square, there is no product x1 x2 like that. So this is called a linear system. For such linear system, so origin is a fixed point. Nature of the fixed point is determined by the nature of the eigenvalue of eigenvalue lambda 1, lambda 2. This is given by a plus d, that is trace of the matrix, then plus minus, this is root over a plus d, that is trace of the matrix square. So square minus 4 times determinant, that is ad minus bc. So this is the 2. So this is the roots. According to the nature of the roots, the fixed points are classified. That is what we have done. But in case of nonlinear system, so what is nonlinear system? The right hand side, this let us open one more window that will be more spacious. One more. Yeah, let us open one more window. So in case of nonlinear system, this dx1 by dt, so it is a function of x1 and x2, any function. There may be nonlinear term also. Nonlinear terms are involved there. So dx2 by dt, so this is equal to v, v2, say x1 x2. So it is a function of x1 x2 means what? Nonlinear terms such as x1 square, x1 into x2, okay, x2 square, x3 cube, like this. All this can be included here. So if it is linear, then we can find out the matrix of coefficient, and then according to the nature of the eigenvalues we can classify the fixed point. Okay, that is what we have studied so far. But in case of nonlinear system, in case of nonlinear system, so we cannot apply that method straightforward. First we have to linearize this. Okay, that what we are going to do is that, so this function v1 and v2, they are function of x1 and x2. We can expand Taylor series expansion about the fixed point. So this can be expanded in Taylor series expansion. So if the fixed point is xf, this can be written as a v1 of xf. Alright, so xf is a vector, x1 is a real number, x2 is a real number, but xf, xf, this can be a vector, say alpha plus alpha beta. This is a vector form written. So v1 xf, so you can expand this v1. This is a function of x1 and x2 variable. You can expand using Taylor series expansion about the fixed point xf. So according to the Taylor series theorem, this is v1 xf plus x1 minus alpha, then partial derivative del v1 by del x1 plus, and this derivative is evaluated at the fixed point, that is xf. So you can write here xf. So xf means what? Alpha beta. So then so this is first order x2 minus beta, this is equal to into dv1 by del x2, and it is evaluated at a point xf, that is fixed point. So then the second degree term is also there, third degree term is also there, it is going on. So you are neglecting those second degree term, third degree term, all this one, then you have this equality, this, that means this is equal to this one. All right, so the reason we are neglecting the second degree term is because this is a very small quantity, you are expanding about the neighborhood of alpha beta point. That means x2 minus beta is very small number, x1 minus alpha is also very small number. So if you keep on squaring, cubing like that, then still they are decreasing, very very small. So you can neglect that one, they don't have any significant effect to the study of the nature of the fixed point, so those things can be neglected. So then it is a linear, this is, and since xf is a fixed point, according to the definition of fixed point, this is going to be 0, this is 0. So this is now it is a linear, because the power here is 1, the power here is 1. So if you transfer the origin to the alpha beta point, and this is replaced by new variable capital X1, and this is replaced by new variable capital X2 after transferring the origin to the fixed point alpha beta, then this is a linear system. This is a linear system where the coefficients are the partial derivative at the fixed point. So this is how we do linearization. Okay, you just expand the tertiary expansion about the fixed point and neglect the higher degree terms. The reason behind neglecting the higher degree term, I have already explained it. So you have a approximation linear system for a given nonlinear system. Okay, and then once you get the nonlinear linear system, then you can apply the previous results regarding the linear system. Okay, so that means what? After transferring the origin to this point, fixed point alpha beta, and using this one, you get a new variable capital X1 and capital X2. For this linear system, X1, X2, in the new variable capital X1 and capital X2, what is the fixed point? 0, 0 is the fixed point. Okay, in the linear system, 0, 0 is the fixed point. Okay, from the nonlinear system, you linearize it, then after transferring the origin to the fixed point, you get a linear system, and the new fixed point is the 0, 0, the new origin. Okay, so this is the fixed point. But in the old system or the nonlinear system, alpha beta is the fixed point. Okay, so the linearization theorem says something about nature of the fixed point 0, 0 of the linear system, and nature of the fixed point of the nonlinear system alpha beta. There is some relationship between the qualitative behavior of the fixed point alpha beta and the fixed point 0, 0 of the linearized system. Okay, after linearization, you get 0, 0 as a fixed point. Okay, before linearization, alpha beta is the fixed point, so alpha beta could be origin also, no problem. Okay, so that is all about nonlinear system and its linearization, and the behavior of the fixed point of the nonlinear system can be understood from the behavior of the fixed point of the linearization system. Okay, so linearized system. All right, so that is all about this lecture. Let us see how we how this one result can be used to ascertain the nature of the fixed point of the nonlinear system. So just let us consider nonlinear system. Okay, this is your nonlinear system. Yeah, let me this one sketch. So this is your nonlinear system, right? The x1 by dt is equal to v1 x1 x2, dx2 by dt is equal to v2 x1 x2. So this v1 is a function of x1 x2, so nonlinear term are included here also, that is x1 square x2 square x1 x2, such type of terms are there here also. So that is why it is called nonlinear system. And suppose xf, this is a vector, okay, so vector form. Xf is a fixed point, that is x1 coordinates alpha, x2 coordinates beta, and this is a fixed point of this nonlinear system. You know, to find out the fixed point for nonlinear system and linear system, the methods are similar. Just put the x1 by dt is equal to 0, the x2 by dt is equal to 0, solve the equation, you find the roots, okay, they are the fixed points. So then suppose alpha beta, that is x half, is a fixed point, okay, then according to the definition of the fixed point, v1 of alpha beta is equal to 0, v2 of alpha beta is also 0. So you can write it in vector form like this, v1 of xf, okay, so v1 of xf is equal to 0 and v2 of xf is equal to 0, because this can be convenient for us in the vector form also, you can write like this, okay. So vector form of the fixed point is, you know, xf is equal to alpha beta. So this is your fixed point. Then now let us use the Taylor series expansion, okay. So first order Taylor series expansion gives you first order, means second order square term, cube term, all are neglected because they are very, very small. They don't have any significant effect to the study of the nature of the fixed point, okay. So then v1 x1 x2 is equal to v1 x, you know, in a vector form, you know, this writing x1 x2 again and again is not very convenient, so you can write in vector form like this, just simple x that denote the vector x1 x2. So v1 x1 is equal to v1 of xf, okay, you are expanding about the fixed point xf, so you have to write this one first term plus x1 minus alpha dv1 by del v1 by del x1 xf, okay, plus x2 minus beta del v1 by del x2 xf, other terms are neglected. So this is first order Taylor series expansion. Similarly for v2 also you can write like this, v2x, this is equal to v2 xf plus x1 minus alpha del v2 by del x1 at the point xf plus x2 minus beta del v2 by del x2 at the point xf, okay. So this is, you know, again at a fixed point this v1 xf is equal to 0, v2 xf is equal to 0, all right. So that means what, after simplifying you will get this one, v1 is equal to x1 minus alpha del v1 by del x1 xf. That means this partial derivative is evaluated at the fixed point, the x2 minus beta del v1 by del x2 xf. Similarly you get this equation, okay. So after then what, transferring the origin to the fixed point using the transformation x1, capital X1 is equal to x1 minus alpha, x2 is equal to x2 minus alpha, then the left hand side is, you know, del x1 by del t, in new variable capital X1 you get this one, okay. So here del v1 by del x1 is evaluated at the fixed point xf, and this one, then this is simply, you know, the linear system, because in the new variable x1 there is first degree term, no second degree term, this one also first degree term. So then what is the coefficient matrix? The coefficient matrix is the, you know, coefficient matrix is the partial derivatives, all right. So thus you get the, you know, linear system. So what is coefficient matrix? Let us go back to the window and let us write. So coefficient matrix is here capital A, this is equal to, capital A is equal to del v1 by del x1 and del v1 by del x2 del v2 by del x1 del v2 by del x2. This is the coefficient matrix, and these partial derivatives are evaluated at the point alpha beta, that is at the fixed point you are evaluating, so you get this one. So this is the way how to linearize the given nonlinear system to a linear system. Okay, nonlinear system to a linear system about a fixed point. You have to do this for every fixed point. Okay, if you have so many fixed point, at each fixed point you can linearize the system like that, and then study the nature of the fixed point of the nonlinear system. Okay, so what the linearization theorem says that, what the linearization theorem says that, you know, so ultimately you have, you know, linearize this system. So let us go back again to the window and write down what the linearization system. Yeah, let us go back. What the linearization system, you have a nonlinear system here, you know, you have a nonlinear system. So this is del x1 dx1 by dt, this is equal to v1 x. Okay, x1 say x2, let us write in this form, and then dx2 by dt, this is equal to v2, you know, x1 x2. This is your nonlinear system. And then at a fixed point xf, xf, this is equal to alpha beta, you know, at the fixed point xf, this is equal to alpha beta. You can linearize it. Okay, this is in the new variable capital X dt, this is equal to a x, you know, this a you already know it. So for this, you know, this is alpha beta, the fixed point of the nonlinear system, and the corresponding linear system, linearized system, is this one. And for this one, 0 0 0 0 is a, that means x1 is equal to 0, x2 is equal to 0. This is a fixed point for this linearization system or linearized system. Okay, for this linearized system, 0 0 is a fixed point. For this nonlinear system, alpha beta is a fixed point. So we want to study the nature of the fixed point of this nonlinear system. How to do that one? First you have to linearize it. How to linearize it? You know, you expand Taylor series expansion up to first order. Okay, and then evaluate the partial derivative, you will get the matrix A, and then, you know, transferring the origin to the fixed point, you will get a new variable capital X1 capital X2, and then for that linearized system 0 0, that is the origin, is a fixed point. So if this fixed point is a center, okay, for this, you know, if this fixed point is a center, all right, center is a stable fixed point, we have studied that one. If this fixed point is a center, then this fixed point alpha beta can be a center or can be in a spiral center. Okay, spiraling center, right? That is what we have studied. Spiral means spiraling inward, outward also is there. So if this fixed point, this fixed point x1 is equal to 0, x2 is equal to 0 is a stable center or center, then the fixed point alpha beta can be a center. Number one, can be a center. Number two, it can be a spiral. Okay, all right. So that is the one. Otherwise, if this fixed point is stable not, if this fixed point is a stable not, then this alpha beta, this fixed point of the nonlinear system, will surely be a stable knot. Okay, if this fixed point is not a stable, it is a unstable knot, this is also unstable knot. All right, so according to the behavior of the fixed point of the linear system, the behavior of the fixed point of the nonlinear system can be predicted. That is the beauty of this, you know, linearization theorem. All right, so if the fixed point of the linear system is a stable fixed point, the fixed point of the, you know, nonlinear system is also stable. Only the problem arises if the fixed point of the linear system is a center, then it is if it is a center, you know, you cannot completely determine the nature of the fixed point of the nonlinear system. There are two possibilities. The first possibility is that the nature of the fixed point may be, you know, center, And the second possibility is that it may be a spiral fixed point. All right, so that is the thing. The spiral fixed point means what? It may be, you know, spiraling out or spiraling in. That is, there are two possibility in case of center. Otherwise, if it is not a center, okay, there are, you know, this one saddle point. If it is saddle point, it is not stable. All right, so if the fixed point of the linearized system, that is 0 0, is a saddle point, then the fixed point of the non-linear system is also a saddle point. All right, if the fixed point of the this one linearized system is a stable knot, okay, then the fixed point of the non-linear system is also stable knot. All right, so that is how we study the behavior of the fixed point of the non-linear system. First, you have to linearize it. To do the linearization, you have to find out the fixed point and then expand, you know, at a particular fixed point you expand using Taylor series expansion, neglect all the higher terms except the first order term. Right, then you will get the matrix. Then from the property of the matrix, you know, you can understand. First you check it whether the fixed point is a stable or center or not. If it is a center, there are two possibilities. The first possibility is that the fixed point of the nonlinear system may be center. The second possibility is that the fixed point of the nonlinear system is in a spiral, you know, 1. Okay, in other cases, that means if the fixed point is a unstable saddle point, then the fixed point of the nonlinear system is also unstable saddle point. If the fixed point of the linearized system is stable knot, then the fixed point of the nonlinear system is also stable knot. Like that you can study. So let us see some example, then you will understand. Okay, so example is that investigate the nature of the fixed point of the nonlinear system. So this is nonlinear, quite obvious, because x1 into x2 is involved here, nonlinear term here. X1 square is involved, x2 square is also involved. So this is nonlinear system. So you can find out the fixed point, you know, you solve it. This, you put this one is equal to 0 and you put this one is equal to 0. So those part you can do it. I am just writing it straightforward because I don't have much space to write here in this form of, you know, class. I don't want to use much space. So something you can do yourself. I have found out, you know, this 0 0 is a fixed point, -1 minus root 3 is also a fixed point, -1 root 3 is also a fixed point, 2 0 is a fixed point. You can do that one, that part you can do it. Okay, so these are the fixed point. There are 4 fixed point for this nonlinear system. So, and then, okay, so what is your v1? V1 is equal to v1 x1 is equal to x2 plus x1 x2. V2 x1 x2 is equal to x1 square minus x2 square minus twice x1. The matrix of partial derivative is given by, you know, the matrix of partial derivative is given by del v1 by del x1, del v1 by del x2, del v2 by del x1, del v2 by del x2, like this. Okay, so ultimately you get this one. So at the origin, you know, what is a? At the origin you put 0 0, then this is 0, this is 1, this is -2, this is 0. So you get this matrix 0 1 -2 0. This is the coefficient matrix. So for this one, what is trace? You know, trace is equal to 0 plus 0 is 0. Trace is equal to 0 and determinant is equal to 2. So then what is, if trace is equal to 0 and determinant is equal to, you know, this one. So let us go back, and then what is your lambda 1 lambda 2? So lambda 1 lambda 2 sorry this is 2, lambda 1 lambda 2, this is equal to a plus d, that is the trace, and then plus minus, this is a plus d, that is trace square, minus 4 times ad, that is determinant bc, this is, and divided by twice a. So if twice a is okay, 1 here. So if a plus d is equal to 0, the trace is 0, this part is 0. All right, and then this part is also 0. So if the determinant, you know, AD. If determinant is negative, this is going to be positive. If determinant is positive, this is going to be, you know, a negative. That imaginary roots are there. So let us see, what is the determinant. So determinant is plus 2, you know. So since determinant is plus 2, minus of, you know, 4 times 2 is equal to minus 8. So there are complex roots. So the trace is 0. There are pure imaginary roots. The real parts are 0. So then the nature of the fixed point is, for this linear system, what is the fixed point of this linear system? 0 0 is a 0 0. The origin is a, you know, for the linear system also, for the non-linear system also, 0 0 is a fixed point. Okay, so for this linear system, the 0 0 origin is a fixed point, and its nature is, you know, center, because, you know, the imaginary part, the real part are 0. The roots are imaginary, the real part are 0. Okay, so you are having pure imaginary root, eigenvalues roots. Therefore the fixed point is a you know, center, stable center. So in this way, you know, in this case there are two possibilities. The fixed point of the linearized system, so trace is 0 here, and determinant is equal to 2. The fixed point of the linearized system is a center. Therefore the origin could be a center or a spiral for the non-linear system. There are two possibilities, I told you. Since the fixed point of the linearized system is a center, there are two possibilities for the non-linear system. For the non-linear system, the fixed point could be a center, or it could be a spiral one. All right, so this is the two thing possible case for the center. This is coming from the linearization theorem. And next, let us see at the fixed point 2 0. This is another fixed point. So you can evaluate matrix like this. At 2 0, what is matrix? At 2 0, this is, you know, x is equal to 2 here. 0 means this is 1 here. So at 2 0, this is 4 minus 2, it is 2, and here it is 0. So it is x2 is 0 0 3, you know, 2 0, like that. So that is the coefficient matrix. So you can evaluate it like that. So it is 0 3 2 0. Here again, sum of the diagonal in 3 is 0. Therefore trace is also 0. Trace of the matrix is equal to 0, and determinant is how much? Determinant is negative, minus 6. So therefore the fixed point of the linearized system is a saddle point, you know. Here it is a saddle point. Okay, so you can easily understood that one. It is a saddle point. All right, because why? If the determinant is, you know, negative here, so minus 4 times minus 6 is equal to 20 plus 24. Then its roots are, you know, plus minus. There are two roots. One is positive, another one is negative. If one is positive, another one is negative, that is a saddle point. It is unstable saddle point. Okay, so for the linearized system 0 0, the origin, you know, this is the fixed point for the non-linear system. For the linearized system 0 0 is a fixed point. Okay, so this fixed point is for the linearized system, and it is a saddle point. It is not stable. So therefore, according to the linearized system, what it says that this fixed point for the non-linear system is also a saddle point. Okay, is also a saddle point. That is the beauty of, you know, linearization theorem. So this is the fixed point for the linearized system in the new coordinate system, capital X1 X2. All right, and this is the fixed point for the non-linear system. So this fixed point is a saddle. It is unstable. All right, therefore this is also a saddle unstable fixed point. All right, so this is the one. For the rest of the fixed point, you try yourself. Minus 1 root 3 and a minus 1 minus root 3. You can do that one. You first find out the matrix capital A. What you have to do, you have to put x1 is equal to minus 1 here, minus 1 root 3. X1 is equal to minus 1 here, x1 is equal to minus 1, x2 is equal to root 3. All right, then you find a matrix, you know, then from the matrix you find out the characteristics roots. So according to the nature of the characteristics roots, you can determine the nature of the fixed point of the linearized system. So if it is not at center, then everything is, you know, similar. If it is not a center, if it is a center, then the fixed point for the nonlinear system may be center or maybe a spiral. In case of spiral, there are two possibilities: spiraling in, spiraling out. Okay, so therefore for the case of center, there are two possibilities. Otherwise, if the fixed point of the linear system is a stable one, for the nonlinear system it is also stable. If the fixed point of the linear system is unstable, the fixed point for the nonlinear system is also unstable. Okay, so next time I will give you more example. So these two you can try it. After solving that one, you know, you send to me through WhatsApp. I will check it. I will give you mark for. So this could be used as an internal exam also. All right, don't forget to upload your solution. Okay, so this much I want to give you today. Next time I will give you some more interesting example. All right, okay, thank you very much.